So I welcome you. The topic today is Advanced in Understanding Thermal Effects in Rubber. I will give a brief introduction to this seminar. That means 10 minutes, 10-15 minutes. But before I start, I would like to give an announcement. Everybody who has questions can write down these questions in the chat. If we have sufficient time, we will answer to the questions, or the speakers will answer to the questions after the presentation, or we will send emails or other way the answers to your questions. So you see on the first slide the overview about our webinar. The first speaker is Professor Jean-Benoît. He will report about the topic thermomechanical and energetic behavior of elastomer, which that I will show also will be the first chapter in our new book. Then we will have Dr. Will Maas from Enturica. I think everybody who is dealing with fracture mechanics, abrasion wear, and so knows him. It's not necessary to introduce this guy in an extra certain manner. He will report about his chapter that is a review of thermal effects on elastomer durability. And then we have Radek Stoček from Zlin, one of the editors, like also Jean-Benoît and myself, of this new book. He will report about this topic, kinetics of self-heat build-up in carbon black-filled natural rubber. I think that we will end this seminar around in 2 hours. Sorry, I have to go to the next slide. So the background of the webinars. Everybody who was attending the first and the second webinars know that we have started to edit and also to contribute in some chapters to a new book series in Springer Nature in the series Advanced in Polymer Science. In 2021, the book about fatigue crack-prone rubber materials appeared, and in 2023 we could offer the new book Degradation of Elastomers in Practice, Experiments and Modeling. By the way, you see, meanwhile, we have a lot of accesses, and also the impact factor of these books is increasing. That is expressed by the altmetric values. Sorry. So, and now we are happy to announce the brand new book that appeared, I think, 2 or 3 weeks ago. It is available also in electronic form and also as hard copy. And the topic is now Advances in Understanding Thermal Effects in Rubbers. I have here listed the web link to this book if you are interested only in the electronic version. And I also have here listed some keywords about, let me say, the hysteresis effects in rubber materials and components, heat generation, self-heating, heat diffusion, heat build-up, till the demonstration of new testing methods, analytical modeling, and the numerical simulation. There's a nice summary. So I have here some problems with switching from one page to the next page. Sorry for that. In this slide, I have given a very rough overview about the benefit of this book. I think this could be considered as a book that provides a comprehensive overview of the latest developments in the field of thermal effects in rubber. It reports about the physical reason and the background for the heat generation processes. This is a little bit more for understanding all what happens in connection with thermal effects in rubber. Hysteresis is enlightened also from the point of view of physics, and so on and so on. We also report in this book about new developments in recent years on test methods and also the corresponding simulation and modeling methods, physical modeling, numerical modeling, etc. So the final goal should be, of course, also to have in the hand a tool that allows a predictive simulation of self-heating and also of the kinetics of temperature fields in rather complex loaded rubber components. This book also highlights the characterization and modeling of the impact of temperature on the durability of rubber materials and corresponding rubber parts, and it shows also applications regarding the heat generation in especially tire rubber materials. Advanced in Understanding Thermal Effects contains 11 chapters. The first chapter, as already announced, will be now described from the author itself. This is again Jean-Benoît from University of Rennes in France. So I have not to give some information now here in my introduction. The second chapter comes from the University Zlín. This is from the group of Radek Stoček. This is about the transient thermal analytical solution of the heat buildup in cyclically loaded rubber cylinders. This is very interesting. He applies here a new heat buildup tester where you can apply to a cylindrical rubber component bending force, and then you can apply a torsion so that it rotates, and you can measure the temperature inside this cylinder and also at the surface. And this is parallel to this. This is accompanied also to a simulation method, and especially here an analytical simulation method. And then you can compare the curves between simulation and measurements concerning the increase of the temperature towards a plateau versus the time in such a loading process. Then we have a chapter that is also presented in this seminar by Radek Stoček itself. This is about the kinetics of self-heat build-up in carbon black-filled natural rubber, so I need not to report about that. We have a chapter from China, the group of Professor Wang. This is about the thermomechanical behavior of thread rubbers during high-speed friction. They present in this chapter the concept of this high-speed friction test equipment. Parallel to this is also going simulation, a finite element simulation, what happens during this friction process concerning the development of temperature fields. And the final application here in this chapter are aircraft tires. Then we have a chapter similar like in the last books, also from the group of Professor Kaliske from Dresden, Germany, about numerical simulation of these processes of fracture in rubber components. This is the phase field fracture modeling of polymeric materials. And here, especially in that chapter, this is new, parallel to the modeling of the fracture process, also the modeling of the development of the temperature field is presented. This is a rather new combination of developments of the last years concerning numerical simulations. Then, like also in the last book, there is a contribution in the new book from the group of James Busfield in London. This is an investigation together with Radek Stoček, of course, because here also the heat build-up tester is applied. And that is dealing with the effect of carbon black on heat build-up and the corresponding energy dissipation in the material. You see here on this slide a diagram with some points. This is surface characteristics, the specific surface, and the internal structure characteristic of different carbon blacks that are used in rubber industry, especially tire industry. And on the right side, you see the equipment where the corresponding compounds with these carbon blacks were investigated and compared, and also hints are given which carbon blacks have a high, let me say, resistance against temperature evolution and so on and so on. Then you see another chapter that is, sorry, that was too much, that was written by the group of Konrad Schneider here from the Leibniz Institute of Polymer Research in Dresden, that is dealing with the characterization of crack propagation in natural rubber under complex loading conditions using thermographic methods. Especially here, biaxial testing equipment was applied. There were some situations, especially investigated, like splitting of cracks. You have then double cracks of different shapes, and parallel to the fracture mechanical characterization, to the characterization of the crack propagation, also the development of the temperature fields in these corresponding crack tips of these relatively complicated crack pattern situations is examined. So last but not least, we have some contributions, some chapters that are also dealing with the, let me say, polymer physical characterization and modeling of these problems of temperature effects. This is a chapter from Professor Heinrich. He is applying here, let me say, more or less pure physical models to understand what happens on a local space inside a material when it is applied to an external load, especially to an external cyclic load. He is also doing some, showing some results concerning MD simulations, so that you have under your view also the you have the view to understand better what is the contribution from specific interactions between the fillers that are bridged with specific polymer chains. This is here visualized in this graph. So last but not least, also another contribution from the Leibniz Institute of Polymer Research in Dresden, together with researcher from DC in Geesthacht near Hamburg. This is a topic about the deformation-induced structure and temperature evolution of natural rubber, characterized by advanced in situ experiments. First author is here Eric Euchler, who is here very active in the moment with these techniques. This sketch shows you that you combine here several experimental approaches, like the white angel X-ray scattering, the small angel X-ray scattering. You can also measure parallel to these scattering experiments, of course, the mechanical behavior of this material, especially under cyclically loading experiments. And of course, because this is a must here, because of the headline of this book, you must also follow the evolution of the temperature, where crystallization appears, decrystallization, and so on, structural rearrangements, and so on and so on. Then we have a chapter, this is a review chapter by Professor Breitkopf, also from the University of Dresden, about theoretical and experimental characterization of heat transfer in polymers and elastomers. It describes the different approaches to measure heat transfer and heat capacity, and also this chapter describes in a very good manner what is the reason of heat transfer, for example. I think not everybody knows that this can be described in the concept of so-called phonons, similar like photons. That means the lattice vibrations in the systems can be considered as quantized quasi-particles. Now, this is a certain useful background which is here described. You see here in one figure the heat capacity of a polymer. I think in that case it is polybutadiene, cross-linked with different amount of sulfur. And you see how it depends on the sulfur content. This is measured, and also is in this chapter presented a simulation how to understand also these measured curves. So, and then we have, of course, the presentation of Wilmars about the review of thermal effects on elastomer durability in this seminar. So I need not to describe this chapter here in advance for that. I hope you will enjoy the seminar. And again, if you have questions, please write these questions in the chat. Thank you again for attending this seminar. And as I heard, just to say this number, as I heard, we have meanwhile around 200 participants in this seminar. Thank you. Time. So I have finished the sharing process. So the next presentation of Jean-Benoît can be started.
Thank you. Hello, everyone. Can you hear me well?
Yes.
Yes, we can.
Very good.
Okay. So, hello, everyone. Thank you for joining this webinar for the presentation of our book, Thermal Effects in Rubber. And first of all, I would like to acknowledge, Professor Heinrich, Dr. Stoček, and Dr. Kipschol for involving me in this book project, which was a very, very nice adventure. So my presentation today illustrates chapter 1, which deals with thermal effects, of course, but with a special focus on how to analyze them, and especially by using calorimetry approaches. So this chapter explains how thermal measurements during deformation can be used in a calorimetric approach to characterize the deformation and damage mechanisms. So we will discuss on elasticity, viscosity, accommodation, strain-induced crystallization, and stored energy. And first of all, okay. So the general framework, first of all, if we have a look at the mechanical response of an elastomer filled with carbon black and submitted to this cyclic loading, we can see in the mechanical response different things: nonlinear elasticity, stress hardening at high strains, stress softening, hysteresis loop, permanent set, etc., large deformations undergone, of course. And this complex mechanical response is due to several phenomena that are the entropic elasticity, the interactions between fillers and the rubber matrix, crystallization and the crystallites melting also, and damage, etc. And these phenomena are either exo or endothermal phenomena. And of course, measuring the change in temperature accompanying the deformation is of first importance in order to improve the understanding of damage and deformation mechanisms. And it will be also interesting by characterizing the thermal response to be able to describe and to identify the mechanical dissipation, and by the way, to better describe the thermodependency of constitutive equations. So the first temperature sensor used during the deformation of a rubber specimens was the lips of Mr. Gert, who stated in 1802 and 1802 and 5, yes, as far as I remember, that an increase in temperature is perceived upon stretching a piece of caoutchouc. And then Joule and Kelvin something like 50 years later, stated that that's not complete in the sense that the temperature variations depend, in fact, on strain. And indeed, for the lowest strains, the temperature decreases and increases for higher ones. And in between, a thermoelastic inversion is found. And since this period and this work, and there were works on self-heating phenomenon, but no works dedicated to the characterization of the thermomechanical effects of phenomena such as the accommodation, the softening, and this is viscosity, etc. And this is the aim of the presentation and of chapter 1 in the book. So first of all, I think that we have to discuss on the quantity that has to be used to investigate the thermomechanical behavior of rubber and more generally in materials. So I'm sorry for the presentation. It's not how to say. I had a problem with sharing my screen in the presentation mode. So I think there is no problem, but this is the reason why the slides are full. Okay, each slides are full. There is no animations. So what I wanted here to explain is that if you consider the mechanical response of a natural rubber stretch at a stretch higher than that at which SiC, so the strain-induced crystallization denoted SiC here, occurs, an hysteresis loop forms. Okay, and if you consider the temperature variation response, you have this curve, so during the loading here, and you have a strong increase of temperature due to the strain-induced crystallization, and the unloading here. So the first thing is that you have not the same temperature between the beginning and the end of the cycle. This is due to heat lost by conduction and convection, and because the cycle are not stabilized thermally speaking. A second remark could be done on the temperature gradient between the grips, okay, before and during the test. So there is a heat diffusion due to convection and conduction, okay, during the test, and also possible external radiations, okay. So this means that the temperature variations are not due to the deformation only. That in the case of strain-induced crystallization here, that there is no information, no real information, quantitative information on the kinetics of SiC and on the mechanical softening and on damage. So temperature is not the relevant quantity to investigate deformation processes, especially in the case of non-adiabatic conditions, which is the most of our characterization tests. So what would be a more relevant quantity? So it would be a quantity that is that does not depend on the heat diffusion, and that enables us to identify the mechanical, also called the intrinsic dissipation. And for that, we use a calorimetric approach. So the calorimetric approach consists in transforming temperature in heat, okay, very basically speaking. And the general framework is the following. During the deformation processes, you have reversible processes due to the thermomechanical couplings, thermoelasticity, entropic elasticity, latent heat, etc. You have irreversible processes, okay, that produce mechanical dissipation, so viscosity, plasticity, damage. So you have reversible processes that leads to heat production and heat absorption. This is the same quantity, okay? And the irreversible processes leads to material degradation and heat production. Okay, but both reversible and irreversible processes leads to temperature gradient. Okay, and if you have temperature gradient, you have heat diffusion, so thermal dissipation. And the aim here is to, from the temperature measurements, to remove the diffusion effect. So I mean the convection and the conduction from the temperature measurements by using the heat diffusion equation. And if we are able to do so, we will be able also to carry out energy balances in order to identify the mechanical dissipation. Okay, so this is the general framework. And the first study that evidenced the interest in using calorimetry approach instead of purely thermal approaches was the one due to Ortsmüller in the 70s from the Institute for Polymer in Germany, and that who investigated a natural rubber stretched inside the calorimeter. And the calorimetric response are presented here. And he found heat production that continues for stretch stopped or keep constant at a value that is superior to the stretch at which crystallization occurred. And he found also the continuation of heat absorption even after, just after the removing of the tension. And he said that by investigating the heat as a function of time, it was already possible to learn something about the kinetics of crystallization. So it was the first ideas about the fact that calorimetry considerably improve the understanding of and the investigation of the mechanisms of deformation. And also that, and sorry, I just moved the text, and the crystallization of rubber needs time, but melting also needs time. So it was very interesting to obtain such results at this period. So calorimetry was for him, of course, a better way than temperature to investigate rubber deformation. Okay, so now, and something like 50 years later, with the advent of the imaging systems, we are able to make surface calorimetry by infrared camera, okay, and also during the deformation of materials. So how does it work? You observe temperature variation. Okay, homogeneous or heterogeneous. You have a matrix of infrared detectors with the camera, so you can have the temperature field. The temperature variations are due to the heat sources and the heat diffusion by convection and conduction, and both are linked by the heat diffusion equations that is given here in its local form. Okay, so you have the contribution of the intrinsic dissipation, the thermoelastic coupling, and other thermomechanical couplings. And if you if you measure the temperature, you derive them by time and by space, you are able to identify and to compare what a model could predict. Okay, and you can obtain the heat sources or the heat power density. The condition is that you know the external heat sources here. But it's very difficult to evaluate during our experiments. But what we can do is, if we prevent our experiments to variation in these external radiations, so if they are kept constant during the test, and by using temperature variation instead of temperature, we can remove it from the heat diffusion equations. Okay, so this is the first point. And if we are interested in characterizing homogeneous temperature field, we can define and determine the heat power density or the heat source corresponding by using this simplification of the heat diffusion equation. Okay, so you know the temperature variation, you derive it by time, according to time, and you divide it by a time a parameter which is a time, and that accounts for convection at the surface observed, of course, in case of non-adiabatic conditions. So you have the mass density, you have the heat capacity, so you are able to determine the heat power density. So what is interesting is that if you make the integral of this heat power density over one cycle, you have a result that can be zero if there is no mechanical dissipation. And if it is superior to zero, this is identified to the mechanical dissipation, or the energy corresponding to the mechanical dissipation. Okay. So now we have the tools to try to make calorimetry under stretch. And now we will apply the tools to different situations and to investigate different mechanisms of deformation. So in this example, I shows two types of macromolecules, a natural rubber and a styrene butadiene rubber, filled and unfilled. When I compare filled and unfilled non-crystallizable rubber, we can have, and you can investigate viscosity and some softening effects. When we compare unfilled natural rubber, crystallizing under stress, and non-crystallizing rubber, we can investigate the effect of strain-induced crystallization. I recall it is denoted SIC here. And when we are interested in comparing the response of filled and unfilled natural rubber, we investigate the effect of fillers and also on the viscosity, and of course the interaction of adding filler and strain-induced crystallization. And so we use this type of specimen geometry here, and the loading conditions is a very classical one, 3 cycles at a given maximum stretch, and we have 4 increasing maximum stretch applied. And the first, some words on the experimental setup. So this is a typical one. You have the infrared camera here, a black box surrounding the specimen here in order to keep constant the external radiations. So you have an illustration of what is observed by the infrared camera here. And we measure, this is not a symmetrical test, so we track the zone in the middle of the specimen during the test, okay? And you have the resolution of the camera here and the thermal resolution here, okay? Just for information, but there is not, it's not really changing as the temperature is assumed to be homogeneous. Okay, so first of all, I present here the response of the natural rubber unfilled. So I recall that from stretch ratio equal to 4, between 4 and 4.5 SIC starts, and then we observe an hysteresis loop before at a stretch ratio equal to 2, for instance, there is no hysteresis loop. Okay. So you have here the calorimetric response. So what you can see is that, so lambda 2 here, lambda 5 here, okay, and the higher lambda there. So the loading, the unloading. And what we can see is as soon that the stretch at which crystallization starts is exceeded, there is a dissymmetry in the calorimetric response. This is the explanation is very simple. This is due to the fact that the kinetics of crystallization, so the heat production rate, is different than the melting. So the heat absorption rate during the loading and the unloading. And if we compare the heat produced and the heat absorbed, this is quite the same, meaning that there is a non-detectable with our tool. It's relative to our tool, of course, but not detectable heat produced over one cycle. Why? An hysteresis loop is observed. Okay, and if we compare with a material that is not crystallizing, okay, typically the SBR here, we have the corresponding, so we have not the mechanical response, but I just put here the calorimetric response. So the response is symmetrical, okay? There is a very little shift toward the Y, the positive Y, okay? This is due to the fact that there is only 5 pHr of carbon lax in the material. And you have a very, very small hysteresis loop, okay? And its sources very symmetrical and close to zero. So the conclusion is that you can have an hysteresis loop, okay, in field natural rubber, that is not due to mechanical dissipation, and that is only due to the change in the microstructure, strong changes in the microstructure, typically the strain-induced crystallization. And so we have, of course, to take care when we want to measure the mechanical dissipation from the stress curves. Okay, now I propose to discuss on the effect of fillers, and for that, I just consider the stabilized mechanical cycles. So I have removed the signature of the Mullins effect. And so you have the mechanical response here. You recognize the different stretch levels applied and the calorimetric response. So we make the integral over each cycle of the heat sources, and we obtain the intrinsic dissipation. So we obtain the intrinsic dissipation, okay, which is only due to viscosity. We assume that there is no damage and that there is no contribution of the Mullins effect. Okay? So if we consider and if we plot the intrinsic dissipation versus the stretch ratio, this is just an illustration of what we can do with such calorimetric approach. We can find here, in this case, a linear relationship between the dissipated heat and the stretch ratio. Okay, so this is, of course, of importance when we want to compare and to challenge the prediction of models, viscoelastic models in particular. And as we removed the Mullins effect from the previous analysis, we can consider that the Mullins effect during the first cycles, okay, because the Mullins effect during the first cycles is the total intrinsic dissipation minus the intrinsic dissipation due to the viscosity, because the unloading path are the same, the unloading paths, sorry, are the same, whatever the number of cycles considered at a given stretch ratio. So this is, so you can evaluate, okay, I just I have to say that the intrinsic dissipation can be accurately and theoretically calculated from thermodynamical cycles, okay, for stabilized mechanical cycles and thermal, so stabilized, sorry, mechanically and thermally, okay. This is not the case for the cycles when the material is accommodating, okay. So this is just an evaluation of the intrinsic dissipation due to the Mullins effect. But what is interesting, okay, is that you can see, so of course for the stabilized cycle, the contribution of the Mullins effect is 0, okay? And for the first cycles, you can see for a given stretch ratio apply, for instance, from 2 to 4.5, that there is an increase of the contribution of the Mullins effect for the first and second cycles okay, with the stretch ratio. Okay, and you have also the characterization of the Molin's effect contribution to the intrinsic dissipation for the natural rubber here. Okay, just to illustrate the possibilities that are offered with the calorimetry approach. Okay, so if we focus now on the hysteresis loop and the different contributions to the hysteresis loop. So I recall that often hysteresis loop is assumed to be due only to viscosity. There's a lot of papers on this topic, and this assumption has many consequences for fracture mechanics and for fatigue, of course. And the question that arises is viscosity really the main phenomena involved in the hysteresis loop? Okay, in other terms, is all the hysteresis loop or the energy corresponding to the hysteresis loop converted into heat? Okay. Just several observations to be discussed before going further. Here, I have considered a carbon black filled nitrile butadiene rubber, okay, which is not crystallizing under stretch, and at 3 strain rates. Okay, so I know that of course we have to evaluate viscous effect over several order of magnitude of strain rates, but it's just for the discussion. Okay, and I plot here the mechanical response. So there is very small or undetectable time dependency in this strain range. Okay. The second thing is that we have seen previously, and sorry for these manipulations on the graphs, that there is from a stretch at which crystallization starts, there is an hysteresis loop that forms in the mechanical response of unfilled natural rubber, and not before. And if the material was viscoelastic, of course, the viscoelasticity does not start when the crystallization starts. Okay, so an hysteresis loop can occur without any viscosity. So there is materials that are not so dependent on the strain rate, and also the fact that an hysteresis loop can form without any viscosity. And of course, in the case of natural rubber, okay, if you add fillers, now you have hysteresis loops that are due to strong changes in the microstructure, strain-induced crystallization, and to viscosity due to fillers. And the question is that, okay, there is a contribution of non-dissipative phenomena to the hysteresis loop, but fillers induce viscosity, but can filler and the filler network also contribute to non-dissipative effect to the hysteresis loop? Okay, so of course this is a very important question for modeling fatigue life, crack growth, and of course self-heating. This is why you have a pseudo Taylor-Queeny coefficient that appears in some development and work dealing on the self-heating. And we can revisit and answer and try to answer these questions with the calorimetric approach. So, theoretically speaking, there is 3 phenomena that can contribute to the hysteresis loop. So, thermal dissipation. Okay, but in the case of course, in the case of non-diabetic condition, this is a very small contribution. If you make the calculation, it's relatively small compared to the other terms of dissipation. The intrinsic dissipation due to viscosity and damage, and microstructure changes, as we were talking about the last slide. So strain-induced crystallization, sorry. And change also in polymer chain conformation. This was discussed in the 60s by Fori, effects of topological constraint, etc. Okay, So the question, as I told you previously, is there a non-viscous contribution of fillers to the hysteresis loop? There is one. There is a viscous contribution, for sure, obviously, but is there a non-viscous one? So to answer this question, we need to carry out a complete energy balance. So how does it work? So you have on one side the mechanical response. From the mechanical response, you determine the energy or the power density involved in the hysteresis loop. On the other side, you have the calorimetric response. So overall, you have the integration of the heat source over one cycle, and you can define the energy and the heat power density involved in the intrinsic dissipation by the integration of the heat power density. And of course, you can define then the part of the hysteresis loop that is converted into heat. Okay, so you divide the intrinsic dissipation by the power involved in the hysteresis loop. Okay, or in terms of energy, because you normalize by the same time, in fact, so you can keep the energy to calculate a ratio that corresponds to the energy stored over the energy involved in the hysteresis loop, okay? And the energy stored is the part of the hysteresis loop, the total energy involved in the hysteresis loop, minus the energy corresponding to the intrinsic dissipation, okay? So this leads to the definition of a ratio that is named here gamma SE, SE for stored energy. And if we, so between 0 and 1, when the value of this coefficient is 1, so you have a high storage abilities of the material, meaning that you have a less time dependency of the hysteresis, damping properties with reduced self-heating. And when this gamma SE ratio tends to 0, you have, of course, low storage abilities and more time dependent and more time dependency and more time dependent hysteresis, of course. Okay, so what I plot now is the response. So the energical map or response of different materials. Okay, the first one is an unfilled natural rubber. Okay, so this is a first interesting illustration, because you have an hysteresis loop, so you can calculate this coefficient only from lambda 4, for which an hysteresis loop forms because crystallization starts. Okay, this is and the hysteresis loop is not really dependent on the strain rate. Okay, you have here the energy response of natural rubber, and you remember that we saw that there is no real effect of the loading of the strain rate. Okay, and yes, of course we had to investigate several order of magnitude of the strain rate, but just from these strain rates, you can see that there was no effect on the mechanical response, but there is an effect on how the material use the energy brought mechanically to deform. Okay, meaning that for the lowest strain rate, the material store more energy, okay, than, so at a given stretch, for instance, okay, than for the highest strain rate. Okay, so I think it would be very interesting to go further on the effect and the surrounding of fillers and the effect of the strain rate on the surrounding of fillers and the filler network. So a lot of studies are currently ongoing by atomic force microscopy, for instance. And also, and to finish, we have the energetic behavior of TPU, okay, at different loading rate. And you can see that there is a small effect of the stretch level, okay, on the value of the ability of the material to store energy compared to NBR. And this is why, energetically speaking, the TPU is close to NR. Okay, this is also maybe why there is strong resistance to crack growth of the two type of macromolecular systems. There is a lot of investigations that could be done from an energetical point of view. Okay, so and this is just to finish on the fact that gamma EC can be an interesting parameter to investigate how rubbery materials and more generally materials use the energy that is brought to him to deform. Okay, I just take a few minutes, if I can, to go further on what we can do with calorimetric measurements, especially when we have a specific calorimetric response, and this is the case when the material is crystallizing. Okay, so from and what is complicated here is to link the calorimetric response to the crystallinity when the material deforms. So we did it. So it's a bit small here, but I can zoom in this diagram. So this is the heat source for an unfilled natural rubber. Okay, so you have an exothermal peak here due to the crystallization. And if you consider the calorimetric response if the material were not crystallizing, okay, with the calorimetric response measured, you have the thermal energy due to the strain-induced crystallization. If you have it, you have the temperature variation due to the crystallization. And if you consider that the enthalpy of fusion is the one of crystallization, you can link the temperature variation due to the crystallization to the crystallinity. Okay, so we did it and we compared for the same material in the same conditions, loading conditions, the measurements provided by the calorimetric approach and the X-ray diffraction technique. And this is what we obtained. No? This was a study carried out in collaboration with Pierre-Antoine Albouy. So we were very satisfied of the results. And this is and this illustrates the powerful of calorimetric approaches to go further and to link what happens at a very, very microscopic scale to the macroscopic scale with quantities that can be used in continuum mechanics. This is one of the main interests of such approaches. Okay, and to finish on this presentation, I would like to show you the same calorimetric approach and the determination of the strain-induced crystallinity for several materials, several specimen geometries, but I just show you one here. And we found that under homogeneous loading, mechanical loading, we can have an heterogeneous crystallinity field. And this explains why, by using X-ray diffraction and the measurement of the crystallinity at one point, the spot of the X-ray diffraction, you can have different results from one specimen to another one, but in fact, it's in the same specimen also. And if you compare the crystallinity along the width of the specimen here, so the width is here in millimeter, you have the crystallinity here. So you have several percent of crystallinity of difference between two different zones. And of course, this means that if we make the measurements at one point and another point, we can have a strong difference in the crystallinity. So this is another reason for which such approaches and making calorimetry from temperature field measurements is very interesting and a very powerful tool. So it's time now to conclude. So first of all, characterizing energy involved in the deformation processes is a powerful tool for understanding the behavior of materials, and especially for rubber. Results show that viscosity is not systematically the preponderant contribution to the hysteresis loop. You can keep in mind the results on NBR. And it depends, in fact, on the strain rate range and the stretch range. And of course, we also highlight the consequence and the beneficial effects of the strain-induced crystallization on the mechanical behavior of the material, especially because the strain-induced crystallization is favorable to and promote the energy storage. Okay, you form springs during the loading. Okay, and you destroy these springs at a different rate during the unloading. Okay, so this is what is very interesting. SiC is not homogeneous under homogeneous loadings. This is also one interesting things we can find by using calorimetry from temperature field measurements, and a lot of other conclusions. So I stop there. I just want to thanks once more the co-authors of the book. Thanks again for this very nice adventure. And of course, I thanks all my co-workers at Institute of Physics and our industrial partners. So thank you very much for your attention.
Hello, I'm Will. First of all, I guess I want to thank Professor Heinrich and Dr. Stoček for and Reinhold Kipschall for inviting me to contribute a chapter. It's always hard to make time to write, but I'm really glad I did this because we learned a lot when I did this. We kind of chose as our review topic a review of thermal effects on elastomer durability. When I was a PhD student, I wrote a review many years ago. And of course, temperature is one of the big things that affects durability, but it's been many years since I wrote that review. And of course, as you get older, you learn that there was a lot of stuff you missed. And so the invitation to work on this review was a great opportunity. And my goal in revisiting the subject was to see if I could bring together in one paper as much of the field as we could fit into one paper. If you look through all the topics, it's such a huge field. But that was really what I was aiming at when we did this. And I have to thank my co-author. If you look in the book chapter I've co-authored with Tom Ebbett, who had a career at Goodyear, and now he's with us at Endurica. So here's an outline of my talk. Like I said, I'm going to touch many topics. This is meant to be a very broad overview of all the different things that thermal effects can influence. Obviously, temperature affects the stress-strain behavior. It affects the dissipative character of the rubber. It affects the strength property and the crack growth properties of rubber. As Jean-Benoît has elegantly shown us, it affects the strain crystallization. We know that it can affect aging in the rubber. We know that, and of course, when we're working these problems, we have to think about thermal transport. And there's another class of problems, which I call thermal runaway, that we'll talk about. So that's kind of what we'll try and cover here in the next half an hour or so. So at a high level, when we talk about rubber's stress-strain response, of course, the first thing we always think about is entropy elasticity, where the elasticity of the rubber derives mostly from the fact that it is more likely to find a polymer chain coiled up than it is to find it stretched out. And that simple statement of probability sort of leads to the conclusion that when the polymer chain is stretched out, there's a restoring force, and that's the basic argument that leads to kind of the statistical mechanical version of the Neo-Hookean law, which you can see if you look on the right-hand side of the slide. This set of arguments leads to the idea that the shear modulus in rubber is proportional to the absolute temperature theta, right? So the hotter the temperature gets, the stiffer it gets, if you're thinking about entropy elasticity. Now, of course, that's an ideal circumstance, and in real life, there are other things that go on in rubber. When there's also a temperature effect. Some people have called it energy or enthalpy elasticity, but really the idea is that they're referring to, instead of entropy elasticity, where it's a probabilistic argument, it's more an argument about changing the distance between individual covalent atomic bonds in the polymer chain, right? That doesn't matter when the deformation is small, but when the deformation gets large and the chains are stretched out, then we're starting to observe almost like a mechanical spring on the polymer chain itself, and that has its own kind of temperature dependence that you can observe, so these are the two major categories of response that we can talk about. Now here's there's a large literature around this, but I really liked this paper from a group in China where they made stress-strain experiments at various temperatures. And so on the left, you're seeing for really an unfilled rubber, an example of entropy elasticity, where as you increase the absolute temperature at constant strain, you're seeing an increase of the stress, exactly as we would predict from the classical theory. And then on the right, you're seeing an example of what I'm calling energy elasticity, which is showing a decrease of the stress in the material as you increase the temperature. Now, obviously, things can be very complicated, and so if anybody ever asks you, does the rubber get stiffer or softer when you heat it up? The answer is it depends. In this paper, they give a constitutive law that is temperature dependent, and that if you wanted to have one model that would be able to represent both types of effects, this might be one that you would want to look at. All right. When we're talking about stress-strain effect, we can also not only worry about the reversible elastic behavior, but we also need to think about the Mullins effect, or some people call this damage, right? It's an initial transient behavior that you can observe in the material. And looking at two results here. On the left, you're looking at some stress-strain curves that have been measured at different temperatures. And what you can notice is that the results on the loading stroke have a relatively strong temperature dependence, right? The black is 25 C, so that's when you're cold, and the blue is the 70 C response as you warm up. And what you can see here is that as you go to higher temperatures, the magnitude, the difference between the load and the unload stroke is reduced as you heat the rubber up. Interesting to note that the unload stroke stress strain response is nearly constant with respect to temperature in this case. Another way to represent the same effect that we're seeing on the left is the result on the right. This was from a study we did for some sealing materials. We characterized the Mullins effect for these materials using the well-known Ogden-Roxburgh model, which I'm showing the equations here up in the upper right. If you're using a final element code and trying to model the Mullins effect, you're probably using this model. And what you're looking at in the bar graph is the parameter R of that model, which really, in a way, quantifies the magnitude of the difference between the initial response and the steady state cyclic response. And what I wanted to emphasize with this graphic was the blue bars correspond to a lower temperature. The orange bar corresponds to a higher temperature. In this case, 100 and 175 degrees Celsius. And just like we saw on the left, you're seeing that as you increase the temperature, the Mullins effect is decreasing. I should note that as R gets bigger, the Mullins effect gets smaller. So these two sets of results are really indicating the same kind of thing. All right. Now another topic that we can touch on is the thermal expansion of rubber. And we know that if you have rubber that is unstressed and you heat it up, it will increase in length just a little bit, like other materials. And you can quantify that type of an effect. You can see on the left here, I've got the thermal expansion plotted as a function of temperature. And so if the slope of these curves gives you the thermal expansion coefficient. Now this is, of course, the thermal expansion of the unstressed rubber. When you stress the rubber, the expansion coefficient quickly can become negative, which is sort of underlies the Guff-Joule effect, which was an old paper here from 1935 by W.B. Wygand. Which if you're interested in some history, that would be a really fun paper to read. They built an engine, a heat engine with rubber bands. But that effect is based on this thermal expansion contraction. And in a lot of when we're calculating, when we're trying to predict fatigue life, thermal expansion can be a very important effect because it often leads to either tensile or compressive pre-stresses in your structure, which can strongly affect crack growth rate, right? Tensile stresses tend to be harmful unless you have strain crystallization. Compressive pre-stresses tend to be helpful. So when you're doing a durability simulation, you want to make sure that you think about the potential thermal effects in order to get these effects correct. We can talk about dissipative properties of the rubber, right? The fact that the work input to the material on the loading stroke is always larger than the work that you can recover during the unloading stroke, and the difference between those is what we call the hysteresis, and this is often the basis for. Or this is one way to measure viscoelasticity in the rubber, and this is also the basis for developing self-heating models. So we'll talk a little bit about self-heating. We'll talk about the strain amplitude dependence of self-heating in the rubber. We can also talk about the temperature and rate dependence of self-heating, and I also want to just briefly mention mode of control, right? Stress control, strain control, and so on. So first of all, let's talk about the strain amplitude dependence. And one of the common ways to represent that is by looking at the linear viscoelastic storage and loss modulus. The loss modulus is proportional to the heat rate that's produced in the rubber, or equivalently the area enclosed within the hysteresis loop of the rubber. And on the right here, you're seeing a plot of the storage and loss modulus. The loss modulus is shown in blue. The dots are measurements that we would make typically from a DMA, right? Dynamic. Maybe we would run this in, I think, a double shear type of experiment is typical, although you can do this in other deformation modes as well, and you'll get similar types of curves. The solid blue curve is the prediction of an equation called the Krauss model. I'm showing these equations on the left, and this is a model that fits these type of data quite well, and you can use this when you're setting up. This is one approach to calculating self-heating. If you're using the Endurica solvers, this is the model that we use. This is one of the models that you can use for representing strain amplitude dependence in our workflows. Now, of course, the loss that you generate depends not only on the strain amplitude, but also depends potentially on the temperature and on the cyclic frequency, especially when you have a large range of frequency. And the idea that I'm introducing here on this slide is something known as the Williams-Landau-Ferry equation. And the core idea here is that the rate of molecular motions, right? You should think of rubber as a bucket of vibrating thermally, a bucket of worms in thermal motion, and you could talk about the rate of that thermal motion, right? When the rubber is very cold, there's not much going on. Everything's frozen, let's say. As you heat the rubber up, the rate of those vibrations increases orders of magnitude. And so the plot on the left is a plot of the relative rate of molecular motion as a function of the temperature, which is usually referenced to the glass transition for the rubber. And this equation there is the WLF equation, and that's the equation that we can use to estimate what's the relative rate of molecular motion. Now, once you know the relative rate of molecular motion, then when you're working with problems that have a time scale, right, a certain period per cycle, you can you can make equivalences, and you can build these master curves to describe the storage and the loss modulus of the material. This is an example of one paper group in China, Fanzu Li at Beijing University of Chemical Technology. They made models using the Krauss model, and you can see also this one had a frequency dependence defined, and they actually built a solid cross-section tire and rolled it on a small wheel, measured it with infrared, and using these types of models, you can make very practical calculations that work really well. I'll just point out again that you can use these models. So in addition to the WLF, a simpler model than the WLF is to use this exponential model. So in the case of this paper, they use this simple exponential model where the temperature dependence of the loss modulus depends as an exponential on the change in temperature and the change in strain rate. That's another. So the Endurica code gives you a couple of options for modeling time temperature dependence. Like I say, we can also do master curves if that's the data set that you've got. So in this case, you would make experiments over a range of frequencies, maybe ranging from a couple of hertz up to a couple of 100 hertz. You might do that at 3 or 4 different temperatures, and then you can use the WLF equation to take these curves from different temperatures and shift them into a master curve, which you can then define. The Endurica code allows you to have these defined in a tabular manner. And that's a second option when you're doing these types of calculations. You can read more about that with this paper here that was recently published in Tire Science and Technology. We can talk about measuring dissipation. When you do these experiments, the answers that you get will depend a bit on the mode of control, right? We've already seen that the stiffness of the rubber depends on temperature. And so depending on whether you're strain controlled or stress controlled, the dissipation itself can have a mode of control dependence. So there's this really important idea that we need to understand the mode of control, especially when we're comparing compounds, right? One of the common mistakes that I see people make in industry is, particularly material compounders, is they'll rank compounds based on, let's say, a displacement controlled test, and they'll rank them in order of dissipation. But then in the application, if it's a stress control application, in the application, the dissipations will rank differently because of the difference in mode of control. So you can correct for that using a simple calculation that I've shown here. In fact, if you're using a finite element model, you can calculate a parameter called the deformation index. The deformation index was originally an idea put forward by Shingo Futamura, but you can calculate this. It basically gives you a scale, right? So this deformation index is here. Here I've identified it with the value x. If x equals to 1, you're in strain control. If x equals -1, you're in stress control. If x equals 0, you're in energy control. You can run a finite element model to calculate these deformation indices. And what you find is, for example, in a tire, different parts of the tire are really in different modes of control. So in the tread of the tire, you see blue. That means we're in stress control because you're supporting the load of the tire, which isn't going to depend on the stiffness of the rubber. But in the sidewall of the tire, you're seeing red, where we have strain control because the rubber there is just carried along, and they do whatever the cords do, kind of irrespective of the stiffness of the rubber. So but now near the belt edges where you have a critical location, you find that actually the mode of control is something a little bit more like energy control. So that's the idea there. So now we've kind of talked about stress strain behavior. We've talked about dissipative behavior. Let's talk about strength and fatigue behavior. And this is actually a bunch of topics as well. We can talk about intrinsic strength, tear strength, right? The crack growth rate curve, the crack precursor size, and then of course some people like to use Volar curves, and so we can think about how temperature impacts each of these things. The image I'm showing here is the fatigue crack growth rate curve for rubber, right? So when I say the tear strength, I'm talking about T sub C, the upper bound of the curve. When I'm talking about the intrinsic strength, I'm talking about T naught, the bottom end of the curve. And when I'm talking about the crack growth rate curve, I'm talking about sort of the in-between regime that's typically characterized by a power law slope F. All right. So first, let's talk about intrinsic strength. So this was kind of an idea that was first put forward by Lake and Thomas. And what they said was that if you're going to grow a crack, there's a certain minimum energy that it takes to grow the crack. So, right, and if a crack is going to grow, it means that you have to cut every polymer chain that crosses the plane of the crack. And so if you know how much energy it takes to break one of those bonds, and if you multiply by how many chains there are per unit crack area, that gives you this minimum energy. And we typically denote that energy with T naught, right? It has units of joule per meter squared. And that has traditionally been regarded as kind of a constant that does not depend on temperature. Now, of course, when we do actual fatigue experiments, if you do fatigue experiments at a constant rate of crack growth, you typically notice that the tearing energy does have a strong temperature dependence. And the reason for that is that in addition to having to supply the energy T0 to break the polymer chains at the tip of the crack, the only way that these polymer chains get loaded up to break is if you also load up all the neighboring chains up nearly to break, which produces a lot of viscoelastic dissipation. And so we have this region in front of the crack that we call the process zone. And that process zone is where all of this viscoelastic dissipation is happening. So, and in fact, the dissipation that happens there is so large that usually it overwhelms the T0 contribution. So, if you're up near the TC value, T0 has a value like 50 joule per meter squared. TZ, the contribution from the process zone, that's going to have a value more like 50,000 joule per meter squared. But the traditional way to think about this is that all of the temperature dependence, all of the rate dependence, all of the R ratio dependence that we see in crack growth behavior of rubber, all of that is a function of what's happening in the process zone of the crack. So the intrinsic strength, I think, is a first idealization. It's probably the truest to the existing literature and observations to say that we don't think of T0 as depending on temperature, if at all or very much, which is a bit of an exception to everything else that we're talking about, and so therefore notable. Now, of course, that's the bottom end of the crack growth curve. We can also talk about the top end. And of course, this is where we do see lots of temperature and rate dependence. Just like the viscoelastic properties of rubber follow a WLF type of relationship, a time temperature dependency, you also see that same behavior reflected in the tear strength of the rubber. So here's a plot of the tear strength of SBR at various temperatures and various rates. And you can see this whole idea of constructing a master curve can be used to describe TC measurements. And I've also got, let's see here, some TC measurements for a few sealing materials at lower temperatures and higher temperatures. And of course, the general trend is that increasing the temperature reduces the it reduces the dissipation, and it also reduces the tear strength. And now, of course, T0 and TC are the extreme limits of the crack growth rate curve. We could also talk about what happens in between. And so this is an example from Don Young, who used to work at Exxon, where he made crack growth measurements at temperatures in the range from 0 to 75 degrees Celsius. And, again, we see that increasing the temperature not only reduces the tear strength, but if you're holding at constant tearing energy, it tends to reduce the rate. So as you go from cold to hot, increasing temperature will tend to increase the rate of crack growth at constant tearing energy. On the left, you've got trying to remember what materials I've got here. I guess you have to maybe look in the book chapter to remember. One of these is natural rubber, I believe, and one of these is a chloroprene. So anyhow. But yeah, so this is the typical behavior. It's kind of remarkable that if you look at the slopes of these curves, they aren't much influenced by the temperature, at least in these rows. So a common assumption, if you don't have, ideally you want measurements, but if you're not in a position to have direct measurements, it's usually a reasonable assumption to assume that the power law slope is approximately not depending on temperature. So TC does depend on temperature, T0 doesn't, and F0 is maybe only weakly dependent. All right. Now, in addition to talking about crack growth rate curves, there is one other parameter that's important in fatigue that also does not depend on temperature, and that would be the size of crack precursors, right? All rubbers contain microscopic features that, when you cycle the rubber or stress the rubber, have the potential to grow, right? And this is leads into the whole field of fracture mechanics. Typically, these features have sizes of something in the range from 2 to 200 microns. They come from there's all sorts of reasons why you can have these things, right? They can be part of the recipe. They can be part of the process for making the rubber, but they're there. But generally, you would not regard that these are dependent on temperature. Just a quick example of using a temperature-dependent crack growth rate curve with a crack precursor. This is on the right here. You can see I've listed out some typical properties for the fracture, the stress strain behavior, and the crack precursor size, and the tear strength, power law slope for natural rubber for SBR. On the left, these are crack nucleation results that were measured by Lake and Lindley. Right, the triangles are for natural rubber, which tends to be very, let's say, insensitive with respect to temperature in this kind of test, compared to styrene butadiene rubber, which is the solid black circles, which you can see loses 4 orders of magnitude of life over a temperature range from 0 to 100 C. So if I take the parameters in this blue table, plug them into the Endurica code, you can see we can replicate this kind of behavior pretty easily. And really this behavior is just coming from the temperature sensitivity of the crack growth rate law, right? So in both of these, we've got a precursor size. We're just integrating the crack growth rate law. I've highlighted in yellow the parameter, which we call the temperature sensitivity coefficient, and which you can see for natural rubber is quite a bit smaller, and for SBR is quite a bit larger. Now, when we talk about crack growth behavior, we need to treat the topic of strain crystallization separately from the temperature dependence that we were just talking about a moment ago. We know that the strain crystallization effect is maximized at lower temperatures, and as you increase the temperature, the effect is reduced. What you're looking at on the left is some work that was done by Gent and Lichun Zhang, where they plotted for NR and for BR the crystalline melting point, right, the crystallization temperature as a function of the stretch of the rubber, right? So we're normally say that crystallization happens something like 200% strain, and you can see that at 200% strain, the melting point for these rubbers is getting close to room temperature, right? So that kind of jives, makes sense. In the Endurica code, we represent strain crystallization using what's called the Mars-Fatemi model. You can see this equation up here that defines that it has one version of this. The simple version has one material parameter, FEXP, which I've plotted here as a function of temperature. And you can see that this plot looks a lot like these results from Gent and Zhang. They're plotting the melting point. We're plotting you call it the crystallization propensity, right? But you can see it's maximum at room temperature, and as you heat up the rubber, that the ability of the rubber to strain crystallize is decreasing. Now this same effect is manifest in many other fatigue tests. This is some work from Lecom's group. You can see on the top row, these are experimentally generated Hay diagrams. These show the fatigue life dependence on the x-axis here is the mean stress, and the y-axis is the stress amplitude, right? So these plots just show you contour lines of equal, lines of equal life in the space of stress amplitude and mean stress. And what I want you to notice is there's 3 different maps here, one for room temperature, 23 C, one for 90 degrees C, and one for 110 degrees C. And if you look at the shape of these ISO lines, at room temperature, there's this interesting behavior where the rubber kind of has this, increasing the mean stress in a certain range causes the life to decrease. However, as you increase the mean stress from the R equals 0 case to the R greater than 0 case, what you're seeing is the life actually gets longer as the material strain crystallizes. Now, as you increase the temperature, the shape of these, instead of having this sort of U-shaped character, now you get a bit of an L shape. And then as you get up to 110 degrees Celsius, then the beneficial effect of mean strain disappears. And we've done quite a bit of work trying to model these experimental results. And so on the bottom row, you're looking at the computed Hay diagrams that have been computed just from using this Mars-Fatemi model with a crack growth rate law, right? So if I just represent this temperature effect on crystallization, then I get this set of curves where this is the 23, the 90, the 110. And to make it easier to compare these experimentals with the computed curves, I'm just going to do a little animation here. There you go. And you can I'm just sort of comparing the like and like parts of the curves. In the experiments, they couldn't quite go out and generate the map in its full extent, but of course we can do that computationally. But you can see we are predicting this same sort of knee in the curve here. We're predicting the fact that as you increase mean strain, the life goes up to a point. Eventually it comes back down. And we're also predicting that as you increase temperature, the effect disappears. And so anyhow, so interesting study. So in addition to strain crystallization, let's see. So we've talked about all the different impacts on, crack growth behavior. We also need to think about what happens from a chemistry point of view. Obviously, we know that rubber that's brand new, if you take it out to Saudi Arabia and leave it there for 10 years in the desert, when you come back, the rubber is not going to have the same properties. And so, for example, you might see that the tear strength of the rubber for a tire that's exposed in a hot environment, that tear strength can be decreased because of the aging. And when we're looking at aging, there's a number of models. The simplest model for aging is what we call the Arrhenius law. And with the Arrhenius law, you are really talking about the relative rate of a chemical reaction, right? So if K is a chemical reaction rate, has units like moles per unit time kind of thing. And we're just looking at a relative rate here. But what we see is that that relative reaction rate is governed by an activation energy EA, and it's also governed by the absolute temperature theta, such that as the rubber gets hotter, right, the reaction progresses more rapidly. A rule of thumb that sometimes people talk about is every 10 degrees Celsius is like a doubling of a chemical reaction rate. Now that's a low resolution way to say it, but if you tell me EA, I can more precisely quantify the relative reaction rate. So this is the basis for doing accelerated aging in rubber. And when we do these kinds of things, what we're interested in is looking at how do the stiffness properties of the rubber evolve? How do the crack growth rate properties of the rubber evolve? So this is a plot. This is some results out of Japan showing the hardness evolution at two different temperatures. The red is at 100 degrees Celsius, and the green is at 70 degrees Celsius. And if you use your imagination a little bit, you might make the statement that 25 hours at 100 C produces the same effect in the rubber as, let's say, 175 hours at 70 C, right? It's this idea that at higher temperatures, time goes faster because the chemical rate. So you could have one curve, but two different time scales because of the different temperatures. We see that the fatigue crack growth rate curve itself evolves. So we can think of TC and we can think of T naught as possibly dependent on aging. If you're talking about the Endurica code, we do have procedures for modeling these effects. We use what's called an incremental fatigue solver that allows us to update the stiffness and crack growth properties as a function of time. So you tell me stress and strain, you tell me temperature, you tell me how long the increment is. We calculate a time shift factor based on the Arrhenius law. We update the crack length based on the crack growth rate law. We update the stiffness. And we do this for an increment. Maybe an increment might be 1 month or 6 months or a year. But we update that. Once we have updated material properties, you can execute your structural and thermal jobs, and you sort of iterate this in an incremental approach to accumulate the aging and the damage effects in the rubber. The advantage of this approach is it allows you to model a time-dependent crack growth rate curve. So as we're doing fatigue, we're integrating the crack growth rate curve, but the crack growth rate curve itself can evolve, and that's something that we can model with these approaches. Now, I mentioned aging, and we have to even go a little bit one step deeper than that, because aging will depend on the chemistry, the particular chemistry that's happening. So this is what's called an Ahagon chart. I think the first time they plotted this is this paper right here. But what you're looking at is that when the rubber is new, you're right here on this, right? So this is a plot of the modulus of the rubber, the stiffness of the rubber, versus, in this case, the breaking stress, or you might view this maybe as the tear strength of the rubber, since the precursor size is constant. But what this is showing is that the path that you follow when you age the rubber depends on the availability of oxygen. If you're aging in a lab air environment, then your rubber is going to follow this path where the tear strength is decreasing as the modulus is increasing, right? So the rubber is getting stiffer as you age it in lab air. On the other hand, if you age under nitrogen, you're going to see, you're going to follow this path right here where the tear strength is decreasing, but the modulus now decreases. And then you could also imagine if you age at different temperatures or different concentrations of oxygen, right? So not pure lab air, but maybe lab air blended with nitrogen, then you're going to find yourself following intermediate pathways. So if you're trying to build a model of how a thing behaves under aging, in certain circumstances, you're going to want to take into account the presence of oxygen in the system and the reactivity of rubber with respect to oxygen. So this is a simulation that we just published. This is not in the book chapter, but I included the slide because this is work we just presented at the Tire Society this year. This is work that Mahmoud Assad did. What you're looking at in this plot on the left is there's 4 variables we're tracking, and this is just looking at the evolution path of the material properties for each of several hundred elements in a tire model. So the 4 variables on the top, you see phi. That is the moles of reacted oxygen per unit volume per element. So we're running a diffusion model. We're calculating the reaction rate. We're integrating the reaction rate, and that's the value of phi as moles of reacted oxygen per unit volume. And then the bottom 3 properties here, T naught, TCE. This is the intrinsic strength. This is the tear strength. This is the stiffness of the rubber, modulus E. You'll see 2 curves in each of these charts. The green line is for the case of aging under nitrogen. The red line is for the case of aging under lab air. The blue line is the particular result for that element depending on the concentration of reacted oxygen. And so you can see basically what we're doing is we're using our different aged results to interpolate to find the results. On the right, I've plotted the Ahagon chart. So you're looking at stiffness versus tear strength, stiffness versus intrinsic strength, stiffness versus oxygen concentration. Again, the red is the aerobic, the green is the anaerobic, and the blue is the actual, individual element. There's, like I said, there's a couple hundred here. And if we take all of those results and put them onto a tire model, then you get things like this. So up in the upper left, you're looking at the development of reacted oxygen over about 30 days of tire operation. You can see the outside edges get kind of crispy there. We also have on the upper right, you can see the stiffness of the rubber evolving due to that behavior. You can see on the bottom left the intrinsic strength of the rubber evolving, and on the bottom right, you can see the tear strength of the rubber evolving. In the middle of the chart, I'm showing a plot of the fatigue crack growth rate curve for the belt, the sidewall, and the ply turn-up. That's the three colors over the 30 days. So if you watch the animation, on day 0, they're all showing the crack growth rate curve, the same crack growth rate curve. But as time goes on, they differentiate based on the particular exposure to oxygen that they're getting. So this feature is not in the Endurica code, the production code just yet. We do have prototype code, and this will probably launch sometime next year into our production code. All right. So that's just a high-level overview on aging things. And I can see we've got about 15 minutes. So Radek, stop me if I'm going too far. Otherwise, I'm just going to keep barreling ahead. So a topic that we can talk about is the approaches for doing self-heating analysis. And we like to view this in 3 levels of analysis. The very simplest analysis is a diabatic analysis. And then the next level up would be maybe steady state, and then the most difficult or the most labor intensive would be the transient. But the adiabatic analysis is nice because what you do is you say, hey, I'm going to assume that no heat leaves the rubber part, and I'm just going to say, what's the heat rate? And if I know the specific heat of the rubber, and if I know a critical temperature that I need to avoid, let's say a blowout temperature, right? Then you can basically convert a heat rate into a time to failure, assuming that heat was not leaving the part. And this is obviously not a very high accuracy approach because heat always does leave the part. But the advantage is you don't have to run a finite element model necessarily to evaluate this criterion, and it can give you a very quick evaluation of whether your heat rate is critical or safe. So that's an approach we sometimes use. The steady state analysis is obviously convenient because, well, it's simple because you don't have to think about time dependence. So that's useful maybe in the context of tires. And then the transient, I'll show some examples of that as well. That the transient is necessary whenever you have, let's say, a thermal runaway type situation. Now, of course, when you're looking at thermal transport properties, you not only have to think about the self-heating or the heat rate, but you also have to think about the possible temperature dependence of the transport properties themselves. So this is a plot showing 2 studies. There's actually quite a bit of literature out there about the temperature dependence of thermal conductivity. And just like everything else in rubber, it's kind of a complicated story. If you look at the gum rubber, you see a very slight dependence or a slight maybe increase of conductivity with temperature. And on the other hand, if you start loading the rubber with carbon black, which is more conductive, obviously the carbon black increases the conductivity, but the temperature dependency becomes stronger with carbon black as well. So you can see these kinds of effects, and it depends on the type of carbon black. It depends on all sorts of stuff. But these are some examples that you might consider. The specific heat, it's the same story, right? So if you have unfilled rubber, unfilled natural rubber, the specific heat tends to increase with temperature. EPDM actually decreases with temperature. And on the right here, I'm showing a specific heat for different loadings of carbon black. The unfilled rubber is at the top. As you put in more black, you're seeing the specific heat is decreased. Thermal runaway. So, when we talk about fatigue, we're talking about crack growth. Thermal runaway is different from that. It is possible to cycle the rubber so violently that the temperature rises quickly, and you can induce chemical reactions that produce gases that begin to inflate the rubber like popcorn, and you can get an internal bubble that forms, and so this is a separate failure mode that sometimes we need to concern ourselves with. Now when you have this failure mode, you cannot model this only by looking at viscoelastic contributions. In this case, you also need to include an exothermic reaction term for the chemistry that is happening, right? So you're going to have viscoelasticity where you have strain amplitude dependence and temperature and frequency dependence, but the viscoelasticity will typically not be enough to let you model the thermal runaway. You also need to consider that rubber has a certain temperature at which the oxidation reactions get triggered. And what you're looking at here is the exotherm from a DSC experiment. You can see it at about 200 degrees Celsius. You start to get this exothermic stuff. And it's a little bit complicated as far as heat rate versus temperature. But the point being that once you reach a certain temperature, the chemistry starts happening and you release a bunch of heat into the rubber, which will cause a very rapid temperature rise. Now, I mentioned the adiabatic criterion for modeling thermal problems. So again, if you know your heat rate, and that could be just the viscoelastic part, or if you're looking to avoid thermal runaway, you would add in your exothermic heat rate here as well. But this allows you to calculate, if I know Q dot, and if I know specific heat intensity, and if I know what my critical temperature is, let's say, 200 degrees Celsius, you can then calculate a time to blowout. And that's really just kind of linearly extrapolating the initial heat slope of the curve. And if this time is, if you calculate your heat rate and you find that TB is 1 minute or 10 minutes, you might, think that you're at risk of a catastrophic failure. If on the other hand, this time is very long, then probably, the extrapolation is not going to be very relevant. But for problems where you have a very fast temperature rise, this is a good back of the envelope to check. So to look at these kinds of problems, we use the Coesfeld and heat buildup analyzer. It's a cylinder that we bend, and we're spinning the cylinder. And as we're spinning it, we set up a tension compression fatigue cycle, which leads to dissipation, and which leads to self-heating of the rubber. And we can measure the internal and the external temperature on this specimen and plot it as a function of time. And here's typical results. Now this is an example that does not have the thermal runaway. So in this example, you're looking at the let's see, you're looking at the internal and external temperatures for two different conditions. So the purple is for 500 RPM, the red is for 1,000 RPM, and this is the specimen. What's really wonderful about this specimen, the specimen does have a hole where you can insert a temperature probe, and the temperature probe is right on the neutral axis of bending. So that temperature probe does not really change the stress strain fields in the specimen very much. You can see that in these stress strain fields that really aren't influenced by the hole. Right. If you think of beam bending, this hole changes the moment of inertia of the beam by less than 0.4%. So it's very convenient that way. And now, if we want to do steady state temperature calculations, we might do something like this, where we do a structural finite element model, a heat rate calculation. Once we calculate heat rates, we can feed a thermal finite element model. Of course, when you do this, you want to take account of the temperature dependence of the heat rate. And so you're going to have to do a few iterations. And once that converges, then you have a steady state temperature field. So here's an example of a paper again out of the BUCT group looking at steady state temperatures in a truck leaf spring. In these bar charts, you can see the comparison of the experiment on the left with the simulation on the right for 3 different designs of these truck springs. So anyhow, now that's an example of the steady state analysis. The third level for self-heating would be fully transient, and the Endurica tools can do either coupled or uncoupled. This slide is showing the uncoupled workflow. First, you do the structural analysis, then you start up your transient analysis. You calculate your heat rates for the current moment, and then you update your structural, and then you just update the heat rate, update the structural, and so on. March the solution through time to get to the end. And there's a couple examples that we talk about in the book. One of the examples in the book is this transient thermal analysis of a tire that is on the high speed rating test, right? So in the government test for giving tires a speed rating, there's a schedule of loads and speeds that the tire has to survive. And so in these simulations, we simulated all those different tire speeds, and we calculated the heat up of the tire through this test. The first part of the test lasts quite a while and is kind of steady state, but the final part of the test, when we go from 160 to 300 kilometers an hour, each time step is only 10 minutes. So that's kind of a transient problem. You can see here the temperature versus step in the test. The first part of the test, we have obviously a temperature rise as you increase the speed on the tire. At a certain speed, you hit a standing wave in the tire, and at that point, you see the temperatures really take off non-linearly. So that's one example. We can also use the transient workflow to calculate thermal runaway. So this is the Coesfeld bending experiment, and you can see the midsection here inflating because of this thermal runaway. Where you see white exploding out, that's north of 200 degrees Celsius on the specimen. And this is a thing that using the again, this exothermic model, we can model that. So again, you kind of follow this workflow of updating the structural and thermal models with heat rates that reflect the current conditions. Now this is the material definition for our exothermic model in Endurica. You define a trigger temperature theta x, right? The exothermic trigger reaction. So here we're going to call that something around 200 degrees C. And then once we trigger this, instead of trying to model the detailed DSC curve, we just give it an average heat rate when you exceed theta x. So that's the model that we'll use. So here's kind of the simulation of that thermal runaway experiment. Since this is the thermal model, you're not seeing the structural deformation, but that's modeled in the structural model. So on the heat rate, you sort of arrive at a steady state, and at a point here, you can see you do end up triggering the thermal runaway, and you see the heat rate suddenly shoot up where we hit the exothermic reactions. That's the heat rate distribution. Here is the temperature distribution. And and then here's the plot of internal and external temperature versus time. The dotted line is the experiment. The solid line is the simulation. And you can see now we're capturing not only the general trends overall, but we're also capturing the upturn at the end. So anyhow. So that's where I'll stop for today. So hopefully we can see that obviously thermal effects are common. Almost anything that you do in rubber is going to have a temperature dependence, and maybe that's not surprising. What is surprising is that there isn't one rule that covers everything. Fortunately, there's experiments we can do to measure all of these different effects, and there's tools we can use to simulate these. And it's really just a matter, when you're an analyst, it's a matter of exercising a little bit of judgment about which things are important to include in your work and which things you can safely ignore. So Thank you.
Today, by cyclic mechanical loading, which is the part of this great book, which I really highly appreciate to cooperate together on with Professor Heinrich, Jean-Benoît, and Reinhold Kipschall. It was a great experience for the third time, so I hope we will continue. So here in this chapter, what we were speaking about, so this is about the heat buildup for sure, and I will slightly repeat or extend what Will told regarding the heat buildup analyzer and the measurement. So the motivation and practical relevance we saw very clearly in the Will's presentation, and I will motivate this like follow. So we can here on this picture we can see the tire, which is like say in a steady state, non-rotating tire exposed to the sunlight. We can see that exposed to the sunlight it has 41 degrees of Celsius, and the asphalt roadway has in the same way 45 degrees of Celsius. So when the tire will be rolled, then there will be an increase of temperature due to the viscoelasticity of the rubber material. So when we can see that this was only a short distance running, only to see how it will really increase the temperature. So in the front drive tire, this has increased up to 52 degrees of Celsius, and rear non-drive tire, it was 47. So we can clearly see that due to the dynamic cyclic movement, there is for sure dissipation of an energy and heat rise. So for sure, doesn't matter whether the sun will there will be sunlight or not. However, we will have there heat build up due to self-heating. So here we have another practical example. On the left-hand side, we can see the ceiling, dynamic loaded ceiling, and there is a visible heat build-up inside of the rubber sample. And on the right-hand side, we can see that this simulation from our instrumented cut-and-chip analyzer. One impact hitting the sample, which simulates the hitting of a tire rolling in a hard terrain, and we can clearly see that there is a significantly heat buildup. So let's say rubber products self-heated due to viscoelasticity and the dynamic cyclic loading. That is for sure, we know it. However, we would like to measure precisely. So this is the video which Will showed very clearly, and I am only the last figure, the last state after the blowout, and we can really see how the gases are coming out. So this is really only self-heating due to cyclic loading, and we really, the material can really blow out. So this is amazing what the rubber can do. And on this slide, I would like to say as well. So what can do the self-heating? What can influence the self-heating? That's for sure. This is the mechanical loading and how the structure of the rubber will so interact and heat it inside, and this will mainly be influenced even by the fillers. So and what we have in such a filler, when we will speak about now track tires, for example, these are mainly based on nature rubber and partly on synthetic like butadiene rubber. So we have a nature rubber, and that was exactly the example what Will showed on this video. It was a nature rubber, and nature rubber will really be inflated by the gases due to temperature, which will have more than 200 degrees Celsius, coming up to 300 degrees Celsius. This is an amazing temperature for sure. So, and firstly, after really blowing out, that will really be totally destroyed, and the gases are coming out. So this is even the problem of environment. So this is not when now it's up to date. It's very popular, the topic particle emission from the tire wear. However, this is another phenomenon which really influence environment. This is a gases emission from a tires rotating, or under the cyclic loading condition. And it's for sure a very large issue. Okay, and what is the right procedure to determine the heat build-up simulating the real tire loading condition in lab? So this is not a very easy to answer, because the tires and other materials for sure as well, how this is an example on tire now, these are multi-axially loaded, and therefore there is not possible to simulate this phenomena only by some uniaxial tensile or dynamic tensile movement. So it needs to be very close to the reality. We need to really simulate the multi-axial loading condition. So, and therefore we developed this heat build-up analyzer, which we'll show as well in his slides, and which is capable to measure the heat build-up inside and on the surface of the sample under the dynamic loading condition. How it's work exactly, more details about it. We have the cylindrical sample. It's fixed on both of ends, and then only for the imagination, when we start to rotate with the sample, there will be no stress inside and no deformation. Therefore, there will be no dissipation of an energy and no heat build-up. We firstly needs to bend in the sample, and then firstly it's to start to rotate. And after this procedure, we will have an oscillating loading, like a compression tension inside, and the temperature will really rise inside. And that's exactly what Will pointed out. We are interested in to measure the temperature inside of the rubber sample, and how the temperature can really rise inside when there is a neutral axis and no deformation, no stresses. So this is because of we clearly know that the heat build-up will firstly rise at the surface, where is the largest deformation, and due to the conductivity of the material, it will be stored inside of the material of the volume, and will increase heat up and heat up. So and finally there will be a larger temperature inside of the volume of the rubber compared to the surface of any product. So and this is now, let's say we have a tension and compression, and as I mentioned, so the temperature will be rising firstly on the surface. This is exactly what happened in a tire, because we have there the largest temperature on the surface of the tire, and then the temperature will move inside and will be stored inside of the rubber material of a tire. So, this is not all. So, because this was only compression tension, to have the multi-axial loading condition, we need to have even the shearing there, and that's on our equipment very easy to realize. Only to shear the material to make a torque V on the one of the end of the sample and control it, and then we would have a tension, compression, and shearing, and we can measure the temperature inside. And the question is, of course, how to measure the temperature inside, and I will show it this later on. Yeah, the equipment, as you saw it previously, I will now only be focused on two details. We have regarding the measurement of the temperature. The temperature is measured inside because there is an temperature sensor, which is a part of the machine. This is a part of the spindle on the right hand side. This is a flexible sensor, you will see on another slides, which is measuring the temperature inside, and then we have an IR camera which measures the temperature on the surface, both temperatures. So this is the geometry of the sample with a hole inside, and the temperature inside is measured exactly in the middle on this radius 2.5 millimeter. The flexible sensor will touch the surface here on the middle. Sample. Yeah, this is the figure now more in detail. Now you can see here in this left-hand side figure, there is this flexible sensor, which is part of the machine, and the IR sensor. And on the right-hand side, there is a fixed sample, this black one, and bended. And the sensor is inside, touching the middle part, and IR sensor measuring the surface temperature. Both will be measured. So now here are the videos. One of them you showed, or you saw already the first presentation. On the left-hand side, you will see now the bending on a different bending angle. This can be up to now 80 degrees. And on the right-hand side, you can see the procedure up to the, let's say, totally rupture of the sample, which will be in a while. So because there is a really very high deformation and very high dissipation of an energy, the material will be very quickly fatigued. You can see now it's really starts to be destroyed, and now it's, yeah, now it is fully destroyed now, the sample. Yeah. And this was not a blowout. This was really a fatigue of the material as well. How I do it to temperature. So sorry, now we will go here. Now you can see here the white line. This is exactly the labeling of the applying of the shearing. This is now, you can clearly see that the material is as well, or the sample is as well sheared. This is not only exactly the line in the neutral axis, however, this is sheared and controlled. We can control up to 10 Newton meter. However, this you will totally destroy immediately by 10 Newton meters. Is really very high. Turkey. So, okay, now this is an, I will introduce now some experimental results which are part of our chapter in the book. And this is exactly based to know how the structure and surface area of different carbon black can influence the heat buildup. So we do different compounds based on nature rubber. 100 pHr of nature rubber with 20 pHr and 60 pHr of carbon black. Here is the volume fraction given, and we apply different carbon black types for 115, 220, 330, 550, and 772. Here on the right hand side, you can clearly see the dependence on a surface area and a structure of the carbon black. So, yeah. Here are the fundamental results from the fundamental properties, only that you can see for these compounds. These upper lines are for the 20 pHr of carbon black, and lower part of the diagram is for 60 pHr of carbon black. What you can see in the green frames, I only denoted the values which are larger than for the another material. So you can clearly see that 20 pHr of carbon black inside of the material independently now speaking about the type of carbon black. However, you can see that for 20 pHr of carbon black you have a larger stress at break, larger strain and break compared to the 60 pHr of carbon black. However, 60 pHr of carbon black has significantly larger modulus M50 and M100, and even the shore hardness is significantly larger. It's well known. Okay, now for these materials, the pain effect, we can clearly see that the storage modulus increases with the increase of surface area and structure of carbon black. This is clearly visible. Even we can see really that the pain effect is very dominant based on the storage modulus, very dominant for the 60 pHr of carbon black on the right hand side compared to the 20 pHr of carbon black, which is very logical. We have a very less carbon black inside, therefore low pain effects. Okay, now loss modulus increases with increase of surface area and structure of carbon black, as well like a storage modulus. This is on the same way. Even we can very clearly again see that this effect is very dominant for the material containing larger amount of carbon black, which is really very expectable. And based on these results, HBU, heat buildup, is expected to increase with increase of surface area and structure of carbon black for sure. So, and this we would like to measure. This we would like to see and approve. So this is the diagram coming from the heat buildup. And what is important to see, it's important to explain and clearly understand we have two curves. One is the measurement of a temperature inside, and one is the this is the full line, and the dotted line is the temperature measured outside or on the surface of the sample. And that's exactly the point. What you can see, firstly, the heat buildup really rise and is created and larger on the surface of the sample, and follow firstly then inside. So that's mean the heat is really firstly needs to be stored inside of the sample and then rise, and then we will come to an equilibrium point over which the temperature inside is larger than outside on the surface of the material. So, and then we can come to the plateau when we are really not speaking about blowout of the material. These are the results from the heat buildup. Now, for the material with a 20 pHr of carbon black, I need to say we measured this for different loading frequencies, which was 8.33, 16.67. So two different frequencies, temperatures inside and outside. And what we can clearly now see, there is for sure a dependence on a frequency. We can see that with a higher frequency, we will have even a higher heat buildup for sure. This is inside is the comparison between the gray one and blue one. Yeah, blue one is always larger than the gray one, so larger frequency. And this is the same as well for the material filled with 60 pHr of carbon black, and then we can see in comparison from the 20 and 60 pHr of carbon black that for 20 pHr of carbon black, we have only slight increase with an increasing of surface area and structure of carbon black, slight increase of heat buildup, of course, yeah, very slight. Oh, there is an increase for sure. However, we have a really dominant increase when this is a material filled with 60 pHr of carbon black. Yeah, you can clearly see we are here up to 120 degrees of Celsius and so on. So very high increase with increasing structure of increase of heat buildup with increasing structure and surface area of carbon black. So there is the opposite trend, let's say, for the number of cycles on which count we really achieve the maximal heat buildup. Yeah, we can see that for 20 pHr of carbon black, this is a more or less constant trend. We are not able to see any increasing or decreasing trend here. However, for 60 pHr of carbon black, the decreasing trend with increasing structure and surface area of carbon black is clearly visible. That's for sure. So that means when the structure and surface area increase of carbon black, we achieve more quickly the maximal heat buildup. So there is a very clear trend. Okay, and now this is a very powerful and helpful curve. We describe this curve even mathematically. This is this description. This has two parts. This is a linear one. This is the first part, and then even what Will showed us, defined by number of cycles and a constant A1, and then we have some nonlinear part, which is described with this equation, defined by two parameters B and A2. So we can now calculate based these parameters A1 and A2 calculated for these carbon blacks filled material for different types of carbon black and so on. So we can clearly see that for both, doesn't matter whether 20 or 60 pHr of carbon black, however, there is an increase of A1 parameter with increase of surface area and structure of carbon black independently on the type, and we have a decrease of A2 parameter with increase of surface area and structure of carbon black. So this is a very clear, let's say, behavior of a different type of carbon black based on surface area and structure of these materials. So this can be very clearly defined, and the trends are very clear how the material like carbon black, like fillers, will really influence the heat buildup of the material. They have a very clear trend trends and can be very clearly predicted by using these technique and methods. This is only now the calculation or calculation and approximation of this curve. The black one is always the measured curve, and the orange one is the calculated curve by using these parameters and equations. So this is only based on one example, based for the carbon black and 550 with 60 pHr of carbon black for the higher frequency. So it's really working. Okay, and here I am on the end of my presentation very quickly, and I would like to conclude very easily. That's mean get exact read on self-heat build-up in lab using heat build-up analyzer. You saw that it's really possible. You saw that carbon black has a very clear trend, can be predicted clearly, and you even saw with that video showing by Will and a figure I showed you later, that is very easily to bring the material to a very unstable blowout, which can be clearly measured, and the thresholds can be measured, and that can be really used for all these predictions. So I would like to wish you an inspirative reading of this book, which I really very much like. And once again, thank you for the co-editors. I enjoy the work together with you and looking forward to the next one. And here I'm really on the end of my presentation, and would like to thank you even for my colleagues and company Cosfeld, even my colleagues at the Thomas Bata University for this kind cooperation. And if you would have any question, then I'm to disposal to answer you by emailing, because I'm sure that Professor Heinrich will inform us that we don't have so much time. So thank you very much for your kind attention.